Hi. Whoa, that was loud. Sheesh. Is that better? Just a recap of where we left off last time. We're talking about routing. And then the first kind of routing algorithm we talked about was link state routing algorithm. And link state is centralized. That means all the nodes have full visibility of the network. And it's an easy routing algorithm because it's based on Dijkstra, which is the shortest path finding algorithm. How are you doing? Hello. Okay, so Dijkstra's algorithm you've come across before. And where I stopped was when we were trying to do this calculation by hand, right? So this is the network we looked at. The basic idea behind link state is quite simple, which is essentially you look at your current cost of getting to a node, and then you compare that with a new cost of getting to the same node, right, via another node, right? And then you pick the best of the two, right? That's essentially what we started talking about. So, and just to remind you of the algorithm, initially you start with, if you're starting at node A, your initialization is that you calculate the cost of all your neighbors, and for all the nodes that you can't get to, you set the cost of infinity, and then you start picking the minimum cost based on what you know, right? And then try to see if you can get a lower cost path from your neighbor than what you think is the current cost of getting to that node, right? So you compare these two values. The cost to a destination is either your old cost, what you know, or a new cost that you can find through your neighbor, right? And you pick the minimum of those two, right? So simple idea, okay? So this is where we stopped off last time. And essentially, we were doing that calculation by hand. And so we started with initializing at node A, and then finding all the neighbors. And then from this list, we pick the minimum cost path. We picked, which is getting to D via A. We add D to the list of paths for which we now know the best least cost path, and then we try to calculate to see if you can find a path to all the other nodes via D, right, which we did. And then now we're here, we have two choices to pick in terms of which node we want to add to the list of nodes for which we know the least cost path. So we can either pick this one or that one. To go with the example that's in your slides, we picked E, right? So that means, so by the second iteration, we know the least cost path to D and E, right? You'll see this pattern. By the third iteration, you'll have 3 nodes. Fourth iteration, you'll have 4. Fifth iteration, you'll have 5. So that's how the algorithm works, right? Every iteration you end up adding 1 node to the list of nodes for which you know the least cost path, okay? Which is this one here, right? So now we're going to try and calculate a least cost path to all the nodes that we know and compare that with the cost that E can provide, right? So in terms of getting to B, my current cost is 2. So if I go via E, so I can get to E with the cost of 2, and then least cost path that E has cannot be better than what I already know, right? So that means I'm going to keep, this is not going to change. Now, let's look at C. My current cost of getting to C is 4, so that's via B, via D, right? So if I go via E, I can get to E with a cost of 2, and then from E, I can get to C with a cost of 1, right? So that means I have 1, 2 to get to E, and E can get to C with the cost of 1. So I have a new cost to get to C via E, right? Sorry? Sorry, 3. Can't add. So 1, 2, 3. So I get to E with a 2, and 2 plus 1 is 3, sorry. And in this case, D is already in our list, so we don't need to evaluate D. E is already in our list, we don't need to evaluate E. Then what about getting to F? Oh, look, E can get to F with a cost of 2, right? So that means I can get to E with a cost of 2. So my total cost of getting to F is going to be 4 via E, right? So now we have a choice of 3 nodes we can look at, and we can pick one of those. We want to pick the least cost path, right, out of the 3 options that we have, so which is going to be B in this case, right? So we're going to add B to the list of nodes for which we know the least cost path. So we have A, D, E, B. And now we're going to look at how to get to all the other nodes via B and see if B can find a lower cost path, right? So that means this is not going to change. If you get to B, B is a cost of 2. What's the least cost path for B to get to C is another 3. That's a 5, but we have a better path, right? 3 is lower than 5. Okay, so that's not going to change. This node's already done. This node's already done. Nothing to do here. In terms of E, so we can get to B with a cost of 2. But what's the least cost path for B to get to F? It's probably going to be, that's an 8, 4, 5. So it's not better than the 4, right? Yeah. So we're going to end up, that's not going to change. So the information that we have is still better than what B can provide, right? Okay, so we're going to keep that, right? So by the end of this round, you'll see that the third iteration, we've identified 1, 2, 3 nodes for which we know the least cost path. By the fourth iteration, we have identified 4 nodes, right? So in this case, we're going to add C to our list of nodes, A, D, E, B, C, and then we're going to see if you can find a better path to all the other nodes for which we don't know the least cost path via C. So we can get a C with a cost of 3. Then the only one we hadn't done is E, but that does not change, right? So we can't find a better path. Yeah? So this is just going to be for E. Are you convinced? Yeah? Okay? So by that iteration, we only have 1 node left for which we don't know the least cost path, and now we do. So we're going to add that A, D, E, B, C, and F, and now the algorithm terminates, right? From F, there's nothing else to go to. Is that clear to you guys? Any questions? Yay. This is the routing table. This is the forwarding table. Right. Is that the forwarding table? So the answer is no. So essentially, so this is the output of the routing algorithm, but you got to still generate a forwarding table. What information should the forwarding table have for A? Do you remember the routing table that I kind of put up on a slide a while back? Sorry? What information does the router use? Destination, but if it needs to go to, let's say from A, I get a packet that goes to F. How does it make a forwarding decision? Where should it send it to next? Huh? I get a packet that's going to F at A. A is a router. How does it determine which link, where should it send to next? Okay, which router should it forward to? To D. How did you guys get D? Because we know that if you want to get to F, we should send it to E, right? Yes? And if you want to get to E, where should we send it to? D, right? So only thing A needs to know is the next hop, which is D, right? So as far as A's routing table is concerned, it has three outgoing links, right? So any packet that comes to A really has, three choices, right? It's either going via this link, or this link. So the ultimate routing table would just tell it what is the next hop, right? Okay, it doesn't need to have all the other information in there. So the routing table will look something like this. So it has destination, and I'm going to call it next hop. So in terms of destinations, we have B, C, D, E, and F. So ideally, these will be the number of the link, right? But instead, I'm going to write the next hop router, okay? So if I want to get to B, that's easy. This says I just send it to B directly. If I want to go to C, where do I send it to? I need to send it to E, but if I want to go to E, I need to send it to D, right? So my next hop is D, right? So if I want to go to D, my next hop is what? Did I make a mistake? If I want to go to D, my next hop is, well, just send it directly to D, sorry. And if I want to go to E, I want to send it to D, right? So my next hop is D. If I want to go to F, I need to send it to E, which means I need to send it to D. So my next hop is D, right? So this is the ultimate forwarding table. So if I get any of these packets destined to C, D, E, and F, my next hop is always going to be router D. If I get a packet that's going to B, I send it directly, right? So that's your routing table, okay? So you can think of this as kind of like a route aggregation, right? Okay? Yeah. All these routes are aggregated to this single link. Yeah. So if at the exam I ask you to use Dijkstra's algorithm and calculate the routing table, don't stop there, get to here, right? Because this is not the forwarding table, but this is well, it's very close to a forwarding table. Okay? Do you understand the difference? Yeah? All right. Any questions? Okay. So all's not well with Dijkstra. We'll see why. Nothing is perfect, right? Unless you're religious. So what's the complexity of Dijkstra's routing algorithm? If you go back to the, let's just say, can I just say worst case complexity here? Just make a note. So if you go back to the, hopefully you've done this already in your data structures and algorithms. So you'll see that if you start at A and if you have n unknown nodes, so in other words, if you start at A and you have 1, 2, 3, 4, 5 nodes for which you need to calculate the shortest path 4, so there's a big loop which goes over all the nodes. So we started at A and we had 1, 2, 3, 4, 5 iterations, right, for the 5 nodes. And in each iteration, we have to do a search, right, to find the minimum cost path, right? Yes? And each time, the number of nodes that you have to search for reduces by 1, right? Why? Because every iteration, we end up finding the least cost path for one node, right? Okay? So that means this search here, right, initially runs for n minus 1, n minus 2, blah, 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 right, up to 1. Okay, this big loop here runs n times, right? So do you know the summation of this series? Huh? I thought it was n plus 1 over 2, right? It's an arithmetic series, right? So the summation of an arithmetic series is, it's like if you want to add 1 to 10, 1 plus 2 plus 3 plus 4 plus 5, right? That's n plus 1 over 2 and gets multiplied by n. So if you did the big O notation stuff, you'll find that this is order n squared, right? So this is the worst case complexity, because you can do better by finding a more efficient algorithm to do the search, like a binary search, in which case we can replace this one with maybe like log n, right? So you can get a better complexity like n log n, okay? So I'm not going to cover that, but you should have already learned that stuff. But if you want to talk about it, you're welcome to see me afterwards, okay? So worst case complexity for Dijkstra's is order n squared, right? Think it's 2 loops, okay? But it can be better by doing a different data structure and making the search faster, okay? So that's kind of bad news in that, you know, it's, and every router has to do that. But the part that I want to bring your attention to is what I called oscillations. So if you have a link state routing algorithm, then here's a problem that can happen, okay? So look at this example here, and imagine that the cost in this case is actually the amount of traffic that's carried. So here, this router is putting on quantity of traffic E. This is 1 unit of traffic. This is 1 unit of traffic. If you like, this is a bidirectional link. So the cost of going from C to B is actually E, because this data is going to A, and it's using this link, but there's no data going backwards, so the cost of going from B to C is actually 0. So there's a bidirectional link with 2 different costs of going in 2 different directions, okay? So this unit of traffic joins B, so this link cost here becomes 1 plus E, because this plus that unit of traffic. And here we have 1 unit of traffic here, which is being sent directly to A, so this link cost is 1, right? Because link cost is determined by the amount of traffic. But look what happens when the routers look at the network. They go, whoa, wait a minute, C goes, there's a lower cost path, because this path here cost E and 1 plus E, but here this path costs 0 plus 1, right? So why route traffic this way? I will route my traffic via D, right? And then B looks at the network, goes, oh, wait a minute, there's 0 here, and 1 here. So going via C is a better path, right? So what happens here? Both C and B ends up routing their traffic this way, right? Yeah, because it's cheaper. But suddenly, the link costs change, right? Because this unit of traffic is going that way, and you have E being sent from C, which adds together to get 1 plus E for this cost, and this unit of traffic adds with that one there to get 2 plus E. Then when you look at the network, well, C goes, oh, wait a minute, actually I can get to A with a lower cost if I go via B, right? And B goes, oh, wait, I can get to A with a 0 link cost. Why am I routing this way, right? So they start rerouting traffic, routing tables change, and you start rerouting traffic that way. So this can happen again and again and again and again, right? So this is of course, it's a demonstrative example, but that's called, that's an oscillating route, right? So this is what can happen in link state routing algorithms. So how can we fix it? What could we do? Or why does it happen? What causes these to oscillate?
Because
has no memory of, yeah, you could say that, but that doesn't really matter, does it?
Some sort of memory though as you were going, saying this used to be quite expensive and now suddenly it's cleared up. Could you say, we won't trust this one because it might get expensive again soon?
Possibly, but you don't know. It's dynamic, right? I mean, with hindsight, yes. But don't have hindsight. Why does this oscillation happen? Sorry? They do, but why does C and B both end up sending that way and then that way again?
Because they don't consider the cost of their own traffic.
They don't consider the cost of their own traffic? Yep. Well, how could we solve it? I love the glasses. Any ideas of solving it? Anyone? How can we stop this from happening? When do they compute their routing tables? What could we change? What are we using as cost? Could we use something else as cost? Would that change? Would that help? Could you think of a different cost metric that causes this problem to go away? Too hard. Yeah, you could use distance. That's pretty much almost the answer. So in routing terms, they're called hops, right? You can use the number of hops. So number of, if you change this, I guess, if you change the link cost to number of hops, that means if I want to get to A from C, I need 1, 2 hops, and if that was my cost metric, it wouldn't happen, right? Because it becomes independent of the traffic. So I guess the simple answer is you shouldn't use traffic as a cost metric for a link state routing algorithm. That's bad. You could use number of hops, which is independent of the amount of traffic, but that may not be what you want to do as an ISP, right? You might want to dynamically change your routes based on the amount of traffic you're carrying through a link, maybe to provide better performance. So typically what you'd find is in link state routing algorithms is number of hops to a destination is used as a cost, right? The other problem you guys will see is that this occurs because all of these guys actually end up computing the routing tables at the same time, right? Like synchronously, right? If for example, C computed the routing table and a little while later B computed it, then this traffic, B might not route the traffic this way, right? So, but unfortunately, this kind of synchronization is what happens in the internet, because when you have a link state change, that information gets broadcast to the entire network, then all the routers may end up recomputing the routing tables, and that might just happen almost at the same time. You can't kind of avoid that, right? It's not saying, oh, I'll just delay my link state update for 5 minutes and I'll take 10 minutes. No, if a change happens, everyone goes, oh, new information, recompute, right? So you can't avoid the synchronicity, right? But what you can do is change the metric you're using for cost, right? As a way around, okay? But the problem is the fact that all of these routers end up recalculating at the same time, right? So what they see in the network is this state rather than a staged event where traffic is increasing from a link to a link, right? Okay. That's Dijkstra. Here's the second one we're going to look at. So this is a decentralized routing algorithm. So I told you guys we're going to look at 2 routing algorithms. One centralized, which is Dijkstra, which assumes that all the nodes have full visibility of the entire network topology, and I go and calculate all the costs in the shortest path. It's beautiful, and every node does it, right? Okay. So distance vector is a decentralized algorithm. So it is iterative because it's not synchronized or anything. So the way it works is essentially it's self-terminating. That is, it continues to update until it gets no new information from its neighbors, right? The way it works is that how it's different is that each node really only communicates directly with its attached neighbors. So compare that to Dijkstra's algorithm and link state routing algorithms, where the nodes broadcast link state information to all the nodes in the network, right? In contrast, what we're doing now is you're just telling your neighbors about any updates. And the neighbors tell the other neighbors. It's like a whisper, right, in a room. You start from a corner, and eventually, after a little while, everyone knows the secret, so as to say, right? Okay? So these guys start a rumor, if you like, and that information just propagates through the network like word of mouth. Okay? So that's the idea. So it's decentralized, no centralized control, right? The reason for that is because routers only talk to their neighbors, and neighbors talk to other neighbors, those neighbors talk to other neighbors, and eventually information gets propagated throughout the entire network, right? How does it work? Okay, so the update is slightly different, right? So what you do is each node has its own row for possible destinations. So it looks like that. So each node has its own row for possible destinations. So if you think of E, which is, where is it? Here, right? So it has a row for each possible destination, so A, B, C, D, and then column for each directly attached neighbor to the node. So E has A, B, and D, A, B, and D, right? Okay. And then what you want to try and do is to actually try to find, you know the link cost to your neighbor, right, which is here, 1, 8, and 2. And then you try to see if you can find a path via your neighbor to the destination that you want, right, which has a lower cost path than what you know about, right? So the idea is that you get your neighbor and then ask your neighbor, what is your lowest cost path to get to the destination I want, right? Okay, and then you add that. Then you ask your other neighbor and go, oh, so I know the cost of getting to you. Do you have a lower cost path to get to A? All right. Then you go ask your other neighbor, oh, because you know this cost. Then you ask your other neighbor, oh, D, I know how the cost of getting to D. D, do you have what is your lowest cost path to get to destination A, right? So if you want to get to destination B, again, you go to your neighbor A and you say, I know the cost of going to A. A, what is your lowest cost path for getting to B? You do the same. What is your lowest cost path for getting to B? You go to D and say, what is your lowest cost path for getting to D, blah, blah, blah. So you continue this, right, iteratively. Okay? So eventually, by asking your neighbors their lowest cost path to get to the destination you want, you end up with a bunch of cost, right, along each row, from which, so eventually, what you end up with a bunch of cost along the rows from which you can pick the best path to construct your routing table. Okay? So this table is called the distance vector table, and the distance vector algorithm, routing algorithm, the job is to essentially construct this table, which will then be used to create the routing table, right? So all this is doing, this formula is doing, is using your cost to get to your neighbor and asking your neighbor its cost, its minimum cost to get to the destination you want, okay? Your cost of getting to the neighbor, asking the neighbor its cost of getting, its minimum cost of getting to the destination, yeah? Is that clear? Okay. So let's have a look at an example. Just keep that up there. So this table is already filled out in your notes. So let's say we pick a couple of examples. I don't know. So if my destination is A, cost of going to A via A is just going to be 1, right? So then I go, I want to go to A, and I'm going to ask B, what's its lowest cost of getting to A? So cost of getting to B is going to be 8, right? And then what's B's lowest cost of getting to A? Is going to be 7, 4, 5, 8. So it should be 7. Can you see a lower cost? 6. That's a 7. This way, right? 2, 4, 5, 6. So it has a path all the way here to get there. So that means you're going to end up with, can't add, is it 14? Right. So I'm going to go to D, right? So I can get to D with a cost of 2. So via D. So I can get to D with a cost of 2. So this is, if you like, B's min cost to A, right? So I get to D with the cost of 2. D's least cost path to get to A is going to be 2, 3, right? Did you see a problem with that? What just happened here? How is D routing to A? This one here. How is... Yeah, by going back through E, right? Okay, so E says, oh, I can get to D with the cost of 2, and ask D, essentially, this question here. What is your minimum cost path to get to the destination I want? And then it goes, oh, wait a minute, my table says I can get to A with a cost of 3, but E has no idea that D's route is through E, right? This is decentralized, okay? So this is called a routing loop. We'll see a problem with this. So, well, it is a problem with distance vector routing algorithms. Link state has oscillation problems. Distance vector routing can lead to loops, right? And this is a classic example, okay? So although I've got a value for 5, now E does not know that D's route is actually via E, but it enters 5 into the table, right? Okay, so I guess it's clear the lowest cost path is my direct link, right, in this case, okay? Let's do another one. Well, these examples you can go through. So I want to get to B. Where's B? B is right here. So my direct cost is 8, right? Can I get my cost to A is 1. Via A is 1. And then from A, the lowest cost path is, I think we said 6, right? So that's a cost of 7, okay? Then check via D. So I can get to D with a cost of 2, plus D's least cost path to get to B is 3, right? So D goes that way, okay? So that's a cost of 3. So that gives me a 5. So now I know I can get to destination B via my neighbor D, right? Okay, so if you just copy the numbers, please do this at home. 4, 11, 2. Then you have 4 and 2, right? Now, is this the routing table? You should all shout out and say, no, damn it. This is not the routing table. This is the distance vector table, right? So from which we will get the routing table. It's easy. This one's really easy. Sorry? Oh, great. So how do we get the routing table? Running out of space. Do I have a blank set? Oh, yeah, I do. Why didn't I use that? I do have a blank slide. So, how do I calculate the routing table? This is... Sorry, I'll get there. So I have destination. Next stop, A, B, C, D. This one's very straightforward. So if I want to get to A, my next stop is just A. It's a direct link. If I want to get to B, the lowest cost path I have is via D, right? D is my neighbor, okay? Remember, we're at E here. At E. If I want to get to C, my lowest cost path is 4 via D. If I want to get to D, just go to D, right? So essentially, that's my routing table, okay? This is the distance vector table, and this is how I generate the routing table from the distance vector table, right? Okay, cool. So again, you can see a bit of route aggregation here, right? For all these destinations, I end up using the same link, right? Now this information will come handy later on in the course when we talk about MPLS, which is a bit later. So this route aggregation means that although I look at all these destinations, I end up sending that packet down the same link, right? Yeah, because I only have 2 options to route. Yes?
Isn't the distance from E to A supposed to be 15, not 14?
What's 8 plus 6? 8, 2.
Plus 6, it's 8 plus 7.
Did we just do this 10 seconds ago? Because isn't that like something like this? 2, 4, 5, 6? Yeah? 2, 4, 5, 6. 1, 2, 3, 4. Isn't this? Is that right?
Yeah, I got it now.
Yeah, cool. Thanks for asking. Yeah, I got confused too when I was looking at it. Thank you. Any other questions? So the question was about how did we end up with this 6? It's this one here, right? Okay? So if I ask an exam question, I ask you to calculate the distance vector table and ask you to show your calculations, I would expect you to write this kind of information down, and then I would expect you to populate the table, right? And not just write the table. Because you don't need to do this to get the table. It's fairly straightforward. And also you can get it wrong and still get the right routing table. And then if I was marking, I'd check all these values are correct. You can make the assumption that you don't pick routes that have loops, no problem, or you can just ignore looping and just pick the route that has a loop. It's okay, right? Like in this case, it's a loop, and we could have ignored it, which is what routers try to do, because you don't want to loop, right? Are we good? Okay, so we end up with the routing table, and this is where you end up. Okay. So final answer, we'll end up looking. Distance vector table, routing table, they're 2 different things, right? Okay. So how does the distance vector routing table, which is decentralized, work? So essentially, each node waits for a change in link cost message from a neighbor. So what that means is if a neighbor is advertising its routing table and advertises a change in its routing table, then you recompute the distance vector table. What that means is that you recompute this part. Okay? If I get a message from my neighbor for example, BOD, telling me that its routing table has changed, I'm going to recompute this table because now I have new information about B's cost to some destination, right? Okay. Then, if recomputing the distance table, which is this one, ends up changing my routing table, it may not, right? It may not end up changing my routing table. I might just change this to 7, but my routing table won't change. I might end up changing this to 100, but my routing table won't change, right? But if I end up changing my routing table as a result, then I have to notify my neighbors of my new routing table, right? Because now I have a least cost path to a destination that I need to tell my neighbors about, okay? But if it doesn't change, then I do nothing, right? Because I have no new information to share, okay? So you recompute the distance vector table. If the distance vector table change results in a routing table change, you advertise to your neighbors, right? Clear? So let's look at kind of the iterative process as an example. So here's what the iterative algorithm might look like, okay? So in this example, it's a simple network. I don't know if you guys can see. So this is X. I forgot to change that to white. And this is Z. Is that any better? Okay. So in this case, so this stuff happens iteratively. Initially, when you start off at X, right? Oops, at X. So X has direct link to Y, so its cost is 2. X is direct link to Z, so its cost is 7. But it doesn't know anything about the cost to Z via Y, right? Because I haven't done anything yet. This is my, if you like, T equals 0 or starting position. Just assume you just turn these things on right now. Boom, right? This is all I know, okay? I only know my cost to my neighbors. And when I don't know a cost, I enter a value of infinity because I don't, maybe the route doesn't exist, right? I don't know, okay? So I don't know the cost via Z to Y. I don't know the cost via Y to Z, so I enter infinity. So all the other nodes do the same. So they enter their, essentially their link cost to neighbor. So yeah, it looks like an edge, right? And then let's assume that at the next time step, so what they're supposed to do is that, oh, I have a new link cost, so I need to tell my neighbors. So let's assume that in the next round, let's pick Y as an example, so this guy here. And then Y advertises its new link cost and says that, oh, I can get to, I have a new link cost to Z. Sorry, I have a link, my link cost to Z is 1, right? So it sends that information off. My link cost to X is 2. So let's assume that this message, so here's a message, right? It's telling its neighbors about new information it has about routing to, let's pick this destination here, Z, right? Cost to Z via Z. And then when this message arrives here at X, X looks along the Z column because I got a message from my neighbor Z, and Z is now telling me some new information. It says that I can get to Y, right, with a cost of, how did I get that? It's from somewhere else. I can get to Z with a cost of 1, right? Okay, and X can get to Z with a cost of 7. So Z can get to Y with a cost of 1, and I can get to Z with a cost of 7. So my total cost is going to be 8, right, here. Yeah. So let's look at the message from, did I just do that right? I looked at Y's, sorry. Sorry, apologize. So I should have looked at the Y column because this is the Z column, right? Let me do that again. Sorry, guys. So I get a message from Y. I apologize, right? So I get a message from y, so I look at the y column, so I can look at cost from y to its destination. So I can get to y with a cost of 2, which is still the best. And then here, y says I can get to z, right, via cost of 1. So this becomes, I can get to y. So I am here, I am x. I can get to y with a cost of 2, and y can get to z with a cost of 1. So I change this to 3, right? And then if I look at this message, here, so z says I can get to y with a cost of 1, so here, right? And then I can get to z with a cost of 7, so that becomes 8, right? And if I look at here, so z says I can get to z with a cost of, this is already there, no change here, so I change this one, and here I change that one, okay? So I end up changing this value and this value, right? This value based on the message from y, and this value based on the message from z, okay? Right? Did I confuse you? I can explain it again. I may have confused you. So the first message is from y, so you look up the y's column, because y is now telling me some new information about its lowest cost. Then I update all the places I can get to via y. I can get to y and z, so I end up updating this information, because I have now found a new path to z via y. I get the message from z, then I look at z's column, then I find that I actually can get a better cost to get to y via z, because z just told me I can get to y with a cost of 1, right? Okay? And I can get to z with a cost of 7, so that's 8. That number here, okay? So this process continues, right, until no new routing information is available, or the routing tables stop changing, right? So essentially, in terms of if you look at this case here, so now actually, if you look at X's routing table is going to change here, right? Because it's found a new lowest cost path to Z via Y. So what will X do? It will now tell its neighbors, right? Because I have a path to Z with a cost of 3 before it was infinity, so that means its routing table would have changed, right? So now it has to tell its neighbors. Yeah. So the full slide is here. So essentially what will happen is initially all 3 nodes will send informations to each other, and then they will update their routing table. And then you'll find that here, because this cost has changed here, Z now updates its neighbors, right? Because his routing table has changed. But look what happens here. Okay, how come there's no new messages from Y being sent in the next iteration? Why doesn't Y send any more information here? Its routing table has changed. Well, we got 8 is changed based on the message from X, 9 is changed based on message from X and Z, right? So why didn't Y send any messages to its neighbors? Any ideas? Sorry? Yeah, go ahead. Exactly. Y doesn't end up updating its routing table. Why? Because its lowest cost path to X is the same. Its lowest cost path to Z is the same, right? So that means its routing table doesn't change. So it doesn't need to tell its neighbors, right? Anything. So there's no messages being sent in this case, right? But if you look at Z, its routing table has changed, right? It used to send via X, now it's sending via Y, right? So that means there's new information that it needs to share with its neighbors, right? So this will continue on